We are going to do the revision of first year syllabus, starting with this chapter, that is atomic structure. Now, atomic structure in the first year you have studied, it comes under physical chemistry part. So it's a very huge chapter, but luckily you have all once again practiced this chapter even in physics. So you might find that these formulas are easy because you have studied it and once again repeated it this year as well. So you might find it easy to solve problems from this chapter. But according to me, in the final paper, NEET paper, what I have seen, rather than asking that you to solve some complicated problems, they mainly focus on the last part of this chapter. That is the chemistry part of this chapter. That is like questions like quantum numbers or the rules of Bose-Hunt's and Pauli's rule and N plus L rule, stability rule, electronic configuration, how to write. Quantum numbers especially, according to me, is the most important thing in this chapter. Quantum numbers. Do you all know quantum numbers concept properly in and out? You should be knowing this concept. It's a very easy and interesting concept actually. And how many orbitals are there? How many electrons are there? Sometimes maybe how many nodes are there? Such type of questions can be expected in the NEET exam. Apart from this, there are many formulas in this chapter. What I'm telling you is that as the chapter progresses towards the end of the chapter, you have more questions which are asked in the NEET exams. Of course, here we have a collection of all the questions. We can go through that. We will also, in this revision program, after every chapter or somewhere in middle of every chapter, I will be sharing with you questions which have been asked from the past 10 NEET papers related to that chapter. So I'm hoping you'll put on the extra effort and solve those as well. Okay, shall we start with this? So first I have made a formula list. So we can go through all these formulas before directly jumping and solving the problems. Ready, children? If you're interested, you can take a screenshot of these things. Okay, there are many formulas in this chapter. So if you're interested, you can take a screenshot. If you already have this formula list, then there are no issues. Okay, so let's start here. I will just go through these concepts and formulas so that we can also recollect them. So this chapter started with Dalton's theory. According to Dalton, he said that the atom is the smallest particle. It cannot be further be divided. But then we found subatomic particles. Within the atom, we found further particles. So that was electron was discovered by J.J. Thomson by cathode ray experiment. And he found out first the E by M value. The E by M value is this number here, very huge number. And then he did Millikan did oil drop experiment, and he found out first the charge and then the mass of electron. Children, is the screen visible to all of you? Yes, right? Looks like you have trouble on your side. Can you please check? Yashasvi, please check. I think screen is visible to others. Okay, then let's continue. So Millikan's oil drop experiment, we found out the charge and mass. Now, this is sometimes not given. It's expected that you know, hopefully you all know that charge of an electron is minus and 1.6 into 10 raised to minus 19 coulomb. Mass is 9.1 into 10 raised to minus 31 kg. This might come in handy in problems. Proton and all, normally they don't expect, or it does not come in problems that much. So it's okay if you don't remember these. So I've marked these as important. If you see, I put stars. Okay, so next going, proton was discovered by Goldstein. I have written its charge and mass also. Coming to neutron, it was discovered by Chadwick, and the charge is 0. The mass is almost similar to that of a proton. Then came the different models. Before going that, this also can be a question saying who has the highest E by M. Because the mass is the lowest for an electron, we say that E by M, the denominator is so low that E by M ratio becomes high. So the electron has the highest E by M ratio. Now, going to the next, different models were proposed for an atom. The first one is Thomson's model, plum pudding model, if you remember, is where he said that electrons are embedded in an atom, just like seeds of a watermelon or plums in a pudding. Okay, next, that was a very basic idea of an atom. Going to Rutherford, who had a much more modern idea, he said that from his alpha ray scattering experiment, he found out that nucleons, that is neutrons and protons, are embedded in a nucleus, and most of the atom is empty and electrons are revolving around this nucleus. There comes the concept of atomic number represented as Z, atomic mass represented as A. So Z is the atomic number. It means that Z means that how many protons are there. Atomic number meaning the number of protons. It can also be number of electrons, but only in a neutral atom. You know that if an atom is charged, if it has plus charge, meaning it has lost some electron. If it has minus charge, meaning it has gained some electron. So electrons or protons match when the atom is neutral. So atomic number is the number of protons. Atomic mass is the number of protons and neutrons. We call that as nucleons. Okay, protons and neutrons together are called as nucleons. So we can write a formula here saying number of neutrons equal to A minus Z, where A is the atomic mass, that is the nucleons, minus atomic number, which is the number of protons. That will give us number of neutrons. So this formula, children, simple formula. This was a question actually asked from this chapter in 2020 paper. So, you know, all the formulas you should know, but basics at least you should know very well. Coming to the definitions, I think you all know that isotopes are atoms having the same number of protons. Isobars are the atoms having the same mass number. That is, they have same number of nucleons. And there is isotones, which have the same number of neutrons. Okay. There is also isoelectronic ions, which is an important concept for NEET. You will also be seeing this term isoelectronic in the next chapter. It means same number of electrons. So these are few concepts that we studied and few constants and few formulas. We have many such slides, children. So one by one, we will go through this. Okay. Then we have a basic formula here. I'm hoping you all know this formula, right? C equal to nu lambda. You might be knowing this in various ways, of course. Nu is frequency and lambda is wavelength. Maybe you know it as nu equal to C by lambda or different ways. It all means the same thing here. Now, wavelength should be represented in meter and frequency in per second, and C, of course, is meter per second. One more important formula here is nu bar equal to 1 by lambda. Okay. Nu bar equal to 1 by lambda. Nu bar is wave number and its unit therefore will be meter inverse, because lambda is length, meter, and wave number is inverse of that. So it will be having meter inverse unit. You can also represent lambda in angstrom. 1 angstrom equal to 10 raised to minus 10 meter. 1 nanometer is 10 raised to minus 9 meter. Similarly, picometer, I have not written here, but picometer, I'm thinking you all know, is 10 raised to minus 12 meter. If you want, you can add that. These are few conversions which are expected that you should be knowing. They won't give you what is an angstrom and all that in the paper. Coming next here, why did we study all these things? That this is the electromagnetic theory or wave theory. So there you studied about wavelength, frequency, wave number, and all those things. You studied about black body radiation and photoelectric effect next. In photoelectric effect, black body, there is nothing that can be asked, so you can ignore that part. In photoelectric effect, you have this formula here. Kinetic energy is equal to h nu minus h nu naught. Photoelectric effect, like the name suggests, is the ejection of an electron when light is incident upon metal surface. So that kinetic energy of that electron will be equal to h nu minus h nu naught. Here nu naught is like one standard frequency. So this frequency is called as threshold frequency. Above this frequency, you will see that there is ejection of electron. You will see photoelectric effect. This whole term h nu naught is called as work function. Work function is the minimum energy. Above this energy, you will observe photoelectric effect. So this question has been asked, not that it has not been asked from this concept, it has been asked, but not very important. Going next, you should be, students, first of all, there's one mistake here. There is no J by S here, it is JS. Just erase that off completely and write it again so that nobody is confused here. In case you took a screenshot, can you please take it again now? Okay, so H is equal to 6.6 into 10 raised to minus 34 joule second. I've just rounded off this figure so that it's easy to remember. 6.6 doesn't sound that bad. This should be enough for you for doing your calculations. Of course, this constant should be given in your paper also. Going next, we have few conversions here. In case you are given normally in this photoelectric effect, you normally deal with electron volt. Energy is given in electron volt. So conversion you might need. If you're getting answer in joule, you need to convert into electron volt. Then this is the value. If you observe, this is actually the charge of an electron, the same value. E is charge here. So 1.6 into 10 raised to minus 19 joule. Coming here, we go to particle theory. Till now, we were studying about wave theory. Particle theory meaning your energy is emitted in the form of packets of quanta. Okay, so packets of energy. This is Planck's theory. So in Planck's theory, we studied that E is equal to nh nu, where n here is the number of photons. So E is equal to nh nu. And of course, this rest of the formula I got from previous formulas, this formula. So nhc by lambda, nhc nu bar, all these are from previous formulas. We next went to spectra, where we studied the Rydberg equation. Rydberg equation is considered as important. Do you all remember the formula? What equal to? There only children make mistake in the first step. So let me go to the next thing here. One last chance for those children who want to take screenshot. You can take a screenshot right now. Okay, so let's go next now. So this is Rydberg equation, nu bar equal to wave number equal to, don't write lambda equal to, nu bar is 1 by lambda, don't forget. So nu bar or 1 by lambda equal to, this number is called as Rydberg constant R, 1 by n1 square minus 1 by n2 square. And then we also have here Z square. Now, if it is hydrogen, then Z is 1. So you don't have to write this. If it's hydrogen, you don't need to write this. That is the case in most of the problems that we solve. Sometimes they can ask hydrogen-like species like helium plus or Be2 plus. That time you have to consider this Z. Okay, so this is the Rydberg's equation. As you see, I've given it 3 stars. It's an important formula. Hopefully you can remember that. And Rydberg constant, I have seen in papers that it's given, but still I would like you to just memorize it and not take any chances. Now this Rydberg constant is in meter inverse, such that you get your wave number in meter inverse. But then if you want in centimeter inverse, then you should not write these 2 zeros. And then you'll get the answer in centimeter inverse. These are all numbers, so it does not matter. All these 3 are numbers. They're going to not have any unit. So whatever is the unit of this, same will be the unit of your new bar. So once again telling you, I have written here Rydberg constant in meter inverse. Now here, one more mistake that children make is they don't know what to take as N1 and what to take as N2. Now, N1 is the lower energy state and N2 is the higher energy state. The number itself indicates that, right? So if we say the lower energy state, we know the different series for hydrogen spectrum: Lyman, Balmer, Passion, Brackett, and Fund. Do you remember? So if I say that I observe the line or the spectra in Lyman, that means N1 is 1. If I say it's Balmer series, that means N1 is 2, or 3, 4, 5 for Passion, Brackett, and Fund. So you should be knowing what is N1 if they tell you the series. Okay. Now, next thing is what is N2. They may either directly give you, or they can say second line in Lyman series. If they say second line in Lyman series, that means N1 is anyway 1. What will be N2? You take that 1 and you add 2 more, meaning 2 above 1. That's what it means. So the answer is 3. So you substitute N1 as 1 and you substitute N2 as 3. You're understanding, children, what I'm saying? So if we say, for example, you're all very silent today, maybe you can answer this. If we say third line in Passion, can you tell me what is N1 and N2 for third line in Passion? Okay, so what happens here is, okay, 11 answers is not bad. Few of you answered correctly here. It means that third line, meaning you all don't have a question, right? N1 is 3. And, Passion meaning N1 is 3. And what is N2? Third line, meaning from 3, you have to go 3 above, plus 3. So N2 would be 6. Getting this? So that's how we should find N1 and N2. Directly, it might not be given. One more thing is sometimes they say limiting line. What does it mean, limiting line? It means the last line. It means you should consider N2 as infinity. If they say limiting line in bracket series, okay, limiting line in bracket series, what will you do? You'll take N1 as bracket series, meaning N1 is 4, right? And N2 you will take as infinity square. So 1 by infinity square you'll get as, you can ignore there. Okay, so that's what you should do, how you should do this type of problem. No, if they are saying third line in Passion, what they mean is Passion meaning N1 is 3, and above this, the line is coming from the third line above. From here, the electron is returning. That's what they mean. So what is this one here? This is 4, this is 5, this is 6. So this is my N2 equal to 6. That's how you count it. Okay. So one more thing they can give here to slightly twist this question is, they can say for maximum wavelength, what will you do? Maximum wavelength meaning, remember one thing, that frequency and energy are proportional, but frequency and wavelength are inversely related. So when we say lambda is maximum, it means energy is minimum. You understanding? If lambda is maximum, energy is minimum. Meaning, say if N1 is 1, what will be N2? What is the least? It could be least number that it could be 2. So you should take the next number like that. Okay. If they say minimum wavelength, meaning if lambda is minimum, energy is maximum. If I take N1 say as 1, what will be N2? Who can answer? You understanding? Question they might not give you directly N1, N2 values. They might say that if maximum wavelength meaning energy is minimum, meaning what? It will just fall from 1 above. From here to here it will fall. That's all. But now I'm saying energy is maximum, meaning from where will it fall? From the topmost line, right? What do we call that topmost line? Correct, it's infinity. So like this also you can figure out a little bit of twist and turns can be asked. So Rydberg equation is important. Understand it properly how to do. Okay, going next here, we have one more. Sorry, this should have come before this because first we learned this. Energy is minus 2.18 into 10 raised to minus 18 z square by n square. And this energy value comes in joule. Okay, but now you can also express this in different terms. So you need to memorize these terms. I'm not sure how much you already know. So minus 13.6 electron volt. One good thing here is everything is some 13, 13, 13 if you're observing. Okay, so maybe it's slightly easier to memorize. Minus 13.6 electron volt minus 1312 kilojoule per mole. Okay, so this was per atom, this is per mole, and minus 313 kilocal per mole. So this is in kilocal. So various ones you should be knowing, but then this is the this part is constant z square by n square, and this constant based on what unit you need, you can vary there. This is an important formula. Now change in energy can be given in the same way like we wrote Rydberg equation. If you see, this looks so similar to Rydberg equation, right? Instead of 1 by lambda or instead of mu bar, when you write mu bar, you should have here 10967700. If you have delta E, then you should have here the energy constant. That's 2.1 into 10 raised to minus 18. This part is the same. Going to the next one here, velocity, sometimes the comparison is asked. So here it was z square by n square. This is how you can memorize by comparing. Here it is z square by n square. Here it is z by n in velocity. In radius, it is completely opposite. It's like n square by z. So you need to put in some effort to remember it. I think energy is the most important. Radius also you can see is little important. Velocity, I've not seen many questions, so you can be okay there. But you need to remember these formulas. Coming to the next fact, now we went on ahead to Bohr's theory. Bohr was the scientist who said about different orbits. So electrons are revolving in different orbits. So that was a concept given by Bohr. And this concept was fine, but it applied only to hydrogen or hydrogen-like species. So you have angular momentum according to Bohr's theory is equal to nh by 2 pi. N here is the shell orbit. Which orbit is it present in? The first, second, K, L, M, N, which is it present in? 1, 2, 3, 4, and so on. So these are the formulas. Anyone who is interested, not taken a screenshot, can take a screenshot. I'm giving you a few seconds. Okay, going next now. This formula can sometimes come in handy, so I will write 1 star here. So ionization energy for hydrogen is equal to ionization energy of helium n square by z square, that is n square by 4, and for lithium, sorry, this is 9, and so on. Okay, so this is one more formula here for ionization energy for hydrogen like species, how you can relate. Number of spectral lines, say if you have N1 as 1 and N2 as 5, how do you calculate total? How many spectral lines do you see? You can use this formula, N2 minus N1, N2 minus N1 plus 1 by 2. N2 is 5. Always remember N1 is the lower orbit, N2 is the higher orbit. So 5 minus 1 is 4 into 5 minus 1, 4 plus 1, that is 5 divided by 2. That is answer will come to be 10. So you see 10 spectral lines. So it's a simple formula. If you remember the, if you have to remember it, that's the only thing. Otherwise, you can also sit and draw it, that it will become complicated. Okay, if you have 5 orbits like this, then you'll see like this few lines, like this few lines, like that you should go on drawing it. Coming to this next formula here, according to me, it's more physics. It's not very important. But still, if you can go ahead, and if you already remember, then it's very good. Potential energy is minus ZE square by R. Kinetic energy is ZE square by 2R. And you can add it, or you can find out the relation between them. I forgot to mark, okay, this is important, and this is very important. Which theory is this? This is de Broglie theory. Now, what de Broglie did is, he said that you have to consider both wave theory as well as particle theory. So here you have a relation between lambda and m and v. So lambda equal to h by mv. So once again, we have Planck's constant here. And this is the main formula. This is very important. Apart from this, you can modify this formula a little bit. So you can put kinetic energy here, because we know that kinetic energy is half mv square. So that formula you use to get here square root 2 kinetic energy into mass. And in case the question is given something in volts, volt, potential is given, then you use this formula, mass and charge and volt you have here. So this is slight modifications, but the first formula is very important. You should all know correctly, lambda equal to h by mv. Okay, let's continue, children. Let's take one chapter at a time. Heisenberg started all his uncertainty business now. So this is where we started heading towards quantum theory, where we are uncertain. We are now saying orbital is probability of finding an electron. That's a space where maybe we are going to find an electron that is maximum in that space. So we cannot exactly say that this is the space or whatever. So Heisenberg's uncertainty principle says that delta x, uncertainty in position, into delta p, uncertainty in momentum, is greater than equal to h by 4 pi. You can just remove the greater than sign, you use equal to sign for problems and stuff. You can modify this, you can take delta v here. That time remember to take mass here. Sometimes accuracy is given, saying they'll say accuracy of position is 0.5%. It will not be so high, it will be less than that, but then some example I've given. Then what you should do, say they said 20 centimeter or something, is x. Then how to find out delta x? You just take 0.5 into 20 by 100. Just like you do percentage stuff. If accuracy of position is given, or accuracy of momentum or velocity is given in percentage, then this is how you need to solve that part. Okay. So once again, if anyone wants to take the screenshot, you can take for this slide as well. Children, it's okay to take screenshots and stuff, but if you want to memorize all this, I would advise you to write it all neatly in one sheet you make, and you try to remember as many formulas as possible. Okay, let's go to the most important concept. I can't emphasize to you how important this concept is. So you can see there are 5 stars now. Okay, so quantum numbers. Let's first see each of the quantum numbers, what it stands for, what it represents. So N represents the shell or orbit. Shell is also called as orbit, to which electron belongs. It can take value 1 to infinity. So you have the first orbit, right? You can't have the 0th orbit. So N will never be equal to 0. So first orbit you have, that's called as K, L, M, and so on. Okay, so 1, 2, 3. So this part, this first quantum number, which is called as principal quantum number N, is same as Bohr's theory, because Bohr had already suggested about orbit. So till there it was coinciding. But the rest of the quantum numbers are a bit more sophisticated, more modern. So let's come to the next quantum number, azimuthal quantum number. L. L represents the subshell to which electron belongs. L takes the value 0 to n minus 1. So 1 less than n. So, and if L is 0, this part is very, very, very important. If L is 0, it is S subshell. If L is 1, it's P subshell. 2 meaning D subshell and 3 meaning F subshell. Now, say for example, I have shell 3. Which is shell 3, children? M. This is my first shell. This is my second shell. This is my third shell. So meaning N equal to 3. Can you tell me what are the values of L now? So what are the values? What we should do? 0 to n minus 1. Everything we should write. We should not only say 2. What we should do? We should write 0, 1 and 2 like this. So L can have all these values, meaning which all subshells can be there. It can be either S subshell, P subshell or D subshell. You're understanding? Meaning when we have third shell, okay, we can write S subshell also, P subshell also, D subshell also. When we have similarly, if we have N equal to 4, what does it mean? What are the values of 0? What are the values of L? 0, 1, 2, 3. What does it mean? The fourth shell, that is N shell, has the values, has subshells, S also, P also, D also, F also. So you can see clearly here so that it is telling us about the subshell to which electron belongs. Now, once you know the subshell, you can also calculate its orbital angular momentum. So you can, that's why this quantum number is also called as angular momentum quantum number. So that's because it's related by a formula here. I have given the formula here. Orbital angular momentum equal to square root L plus 1 h by 2 pi. So you can see the L here. I have used the second quantum number, that is azimuthal quantum number has been used in this formula. Coming back here, let's proceed. The next quantum number is the magnetic quantum number M. This represents the orbital to which electron belongs. So let's just see how to do this. It takes the values minus L to plus L. So if we have S, 0, right? L value is 0. So how many M can we write? Minus 0 to plus 0, that is 0 only. Whereas if you take P, that is 1, L is 1, what can we write? Minus 1 to plus 1, meaning what? Minus 1, 0 and plus 1. These represent 3 orbitals. Okay, so these represents 3 orbitals. Now we consider in all this part, we consider Z as the reference axis. So remember that always, in case it is asked anything related to this, remember that PZ is the one which is considered to be 0. So basically, now you know that if L is 1, M has values minus 1, 0, plus 1. This is the formula. Minus L to plus L. Meaning 3 orbitals are possible. Meaning one subshell. Which subshell is this? P subshell. If you have a P subshell, we can divide it into 3 orbitals. We have been doing that, right? What are they called as? Px, Py, Pz. And this one with the 0 is the Pz orbital. So a little bit further, we can go and say that. Okay. So this is how we can write the values. Pz is 0. Px is plus or minus 1 and Py is also plus or minus 1. So, and spin quantum number tells us about the electron itself. We know that if there are 2 electrons that can be put in an orbital, both will have opposite spin. So we draw like this, remember? Like this. So one of the electron, if it is, we represent its spin as plus half. The other one spin we represent as minus half. This whole quantum number concept is very important, how to calculate, how we can tell whether a certain orbital is possible or not possible. Say, for example, can you tell me whether 3F is possible? What does 3f mean? What is n and what is L? Can you tell me what is n? What is the shell for 3f? Correct. Whatever is this number that we have written here, that itself is the shell. So n is 3, correct? And f meaning, what is L? Very good, all those who are answering. So SPDF, remember, starts from 0, 0, 1, 2, 3. So therefore, F is meaning L will be 3 there. Can this situation, does it sound okay to you? No, it is not okay. Why? Because when n is 3, the values for L are 0 to n minus 1. That is, it can have value either 0 or 1 or 2. It cannot have the value 3. So I can say this orbital is not possible. You might have also observed that we never write 3f. We start writing from 4f. Okay, because for 4f, what will happen? We have n as 4 and L as 3. This situation is fine. This orbital exists. As long as it is lesser than n, that number is fine for L. So this formula is important, this part. Okay, so n minus 1. Let's take one more example. If I have L as 1 and m as plus 2. Okay, n also I will write n is say 2. Is this situation okay? Can this orbital exist? What do you think? So n is 2. Okay, that means the second shell. And L is 1. That's also fine because it's less than n, meaning it is p, right? Okay, that's also fine. But then if L is 1, then m is minus 1, 0, plus 1. So this cannot exist. Plus 2, how it came there, right? So it cannot exist. So that's wrong. Understanding? So this way you should be knowing about quantum numbers really properly. They can also ask you how many electrons are present in something. So say, for example, I'll say how many electrons are present in n equal to 4 and L equal to, okay, 1. How many electrons are present? In this, I have to specify, of course, in the question you should see properly. In this subshell, how many electrons are present? No. In this subshell, how many electrons are present? No. So going wrong here, few of you. So what you have to do is, first of all, figure out which is the subshell. Which is the subshell? We can write 4 here. And what is L equal to 1, meaning P, right? So that means it's 4P. Which is the subshell here? 4P. And in 4P, how many electrons can you put? You can put only 6 electrons. You know that, right? 4P contains 6 electrons maximum. So that's the number of electrons you can put. If the question was only this I have given, only n equal to 4 I have given, and I'm asking, okay, then you will use this formula. That's what you all are telling me the answer. Okay, total number of electrons in a shell, in an orbit, okay, 2n square. So 4 square, that is 6, 4 4s are 16, 2s are 32. That time you'll get 32. This is number of electrons in a shell. Question was how many electrons in the subshell? In the subshell, that is 4p, you can put in 6 electrons. Okay, and orbitals meaning each orbital contains 2 electrons. So number of orbitals in a shell you can count by n square, half of number of electrons. Okay, I think we discussed this enough now. Now let's go further. Notes can sometimes be asked in a NEET paper. So they are actually very easy to remember. Either graphs are given and then you need to identify how many nodes are there. Node meaning the probability of finding an electron is 0. Meaning if you have graphs like this, probability of finding an electron. That means if it is reaching, say if the peak is there like this. Okay, 3 peaks are there, 1, 2, 3. This means probability of finding electron is high. Okay, so peaks are there. That is actually the number of peaks or the number of humps is equal to n, the orbit. Okay, so which orbit is this? You can recognize there are 3 peaks. So the number of n is equal to 3. Okay, shell is third shell. Okay, now how to recognize the nodes? You can see here where it intersects this. Okay, where does it intersect? At 2 places, meaning the total number of nodes is 2. Understanding? So this is how you calculate by looking at a graph. How many nodes are there? Now we also have formula here. So radial nodes, there are 2 types of nodes, radial and angular. Radial nodes has the formula n minus L minus 1. N is quantum number, principal quantum number. L is azimuthal quantum number, the second one. Whereas angular quantum number has the formula only L. Okay. And so total, what will it be? N minus 1. Let's consider the situation, children. 5D I have. How many radial nodes are there in 5D? What will you do? How many radial nodes are there? What you'll do is, n you take, what is n here? 5. This number which is written here as principal quantum number n. So 5 minus, and D meaning what did we learn? D meaning L is 2, because I have L here, minus 2, minus 1. That is, what did we get here? 5 minus 2 minus 1 is 2. Correct? This is radial nodes. Okay. Now, how many angular nodes do we have? L. How many angular nodes do we have? Only 2. Add these 2. Radial nodes, angular nodes, add them. What did you get? How many total nodes did you get? 4. You can also calculate by another method. N minus L minus 1 plus L, meaning minus L plus L gets cancelled. So what you have is only N minus 1. So 5 minus 1. That way also you're getting 4. So this is how you calculate radial nodes and angular nodes. Okay. And I have written here number of peaks is equal to N. That's how you'll find out the shell or the orbits. Okay, coming to this next formula, children, this formula is very, 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 very important, but I have not marked it important here. That's because this formula actually belongs to D block element, kind of belongs to coordination chemistry. Maybe in some other chapters also you have used it in inorganic chemistry, but it starts from this chapter. So it can be considered as a common question. Very important. Almost all papers you will see this formula used. Mu, magnetic moment, equal to square root n plus 2. Here n is the number of unpaired electrons. So n can mean 2 things. Here the n is number of unpaired electrons, where here and all it was meaning the orbit, the shell to which electron belongs. So this is an important formula. This formula I've already explained. Apart from all these things, how to write electronic configuration and the rules are very important. Okay, let's go there. Anyone who wants to okay, you will not leave me, right? The accuracy will not be that high, 99.9%. No, it will be some 0.005%, like that the accuracy will be. Okay. For upcoming tests, we have to refer, portion is huge. Children, this is just 2 chapters. You have to write NEET exam where there is like many times more. So you have to put in more effort here. Trying to make it easier by going through all this before I start with any problems here. Okay, children. So electronic configuration, when we write, we follow these 4 rules. These are very important. Once again, you can see my 5 stars here. So what are most important? Once again, first you do in this chapter, quantum numbers, rules, and how to write the electronic configuration. For some element also they can give, saying this element, write down the electronic configuration, then you should be in a position to do that as well. So Aufbau's principle, basically you can draw a diagram like this. It's very easy to draw. It looks like some type of a rangoli here. You go in an increasing pattern. Once you reach here 4, then go in a decreasing pattern. This much is enough to fill all the elements in a periodic table. Okay, and Aufbau's rule states that electrons are filled according to increasing energy level. Hund's rule states that electrons are filled in a subshell or in degenerate orbital singly before pairing occurs. So here I've written something called as exchange energy. So exchange energy meaning why this is related to why we see that half-filled orbitals are very stable. Half-filled orbitals and completely nitrogen, for example, is stable. That's because of, first of all, distribution of electrons is symmetrical. We can see that 1, 1 each or 2, 2 each makes it more symmetrical, or because of exchange energy. Exchange energy meaning this electron, for example, it can go here, exchange places with this electron. One exchange. It can also go here, exchange spaces with this electron. So 2 exchanges it did. What other things we can do? This can go here. So that is 3 exchanges we can do. Like that, by counting, you can tell that who is more stable. Whoever has the more exchange energy, they are more stable. If you find formula easy to memorize, then this is the formula for exchange energy, n minus 1 by 2, where n is number of unpaired electrons. Say, for example, okay, I think we have an example coming up in the questions. So that example we will take. Number of unpaired electrons, you should consider, if we have, say, for example, 4 unpaired electrons, then 4 into 4 minus 1 by 2. That is, you have 6, is the answer. 6 exchanges can take place. Meaning, if you have 4, like in a D subshell, 1, 2, 3, 4 you have. Okay, this one is empty. Then this electron can go 1, 2, 3. 3 exchanges it can do, plus this electron can do 1, 2, and this electron can do 1 exchange. So 3 plus 4, 5 plus 1. Like this also you can calculate. You don't have to actually remember formula. Pauli's principle states that one orbital can maximum contain 2 electrons, both with opposite spin. N plus L rule is most important of all these rules because it is not very important for PU. It's more important for competitive. So what we use the logic, in fact, I've seen N plus L rule question being asked at least 3 years in the past 5, 6 years, 3 times. So N plus L rule states that higher you have N plus L value, higher is the energy. If it's equal, what does it mean higher N plus L, higher energy? Say, for example, I'm taking 3S and 3P. What is N here? 3. What is L here? 0. What is N plus L here? 3. Here what happened? N is 3. L is 1. P, right? So L is 1. So what is N plus L? 4. Who has higher N plus L? 3P. So who has higher energy? 3P as compared to 3S. But sometimes you'll get same N plus L values. Like, for example, instead of 3S, what if I had 4S? I have now 4S here. So my N is 4 here. My L is 0. So 4 plus 0 became 4 here. So now my N plus L value is same. Here also 4, here also 4 I have. Now what I should do? Just see N. Higher N, higher is the energy, which is higher N here, 4. Okay, so who has the higher energy? 4S as compared to 3P. You can even, by the way, one more thing is higher energy meaning it will be filled later. Lower energy will be filled first. So same question can be twisted and asked who will be filled first? 3P will be filled first because it has lower energy. The same logic is used in our Aufbau's diagram. So anytime you're confused, you can recheck it by drawing the diagram. Whichever is easy for you or both you can do in case you're confused. Okay, so that's our answer here. Aufbau's principle is also in increasing order only, correct? Okay, children, you understood this logic, right? So 6p and 7s once again. Yes, correct. 7s will be at higher energy because n plus l value will be coming the same. So higher n, who has higher n? 7s. That will be of higher energy. So how are the formulas? These are just basic formulas which were there in this chapter. Apart from that, with these formulas, you can form other formulas as well. I have not included them here. I didn't want it to seem a lot. And also there are some complicated formulas as well. The chance of that being asked in the final exam is extremely rare. More and more questions are based on very simple things in this chapter. In chemistry paper, of course, in physics and chemistry, when you're studying, you can go through this chapter in detail. So let's solve some questions here. Try not to look at the answers here. Okay, try to solve it. Okay, children, break in all you're asking. Come on, what's wrong with you? Okay, break is done, right? Let's do this. Okay, this is actually the question that I was mentioning. You have 3D4 configuration. How will you write, children? D subshell. Like this only you will write, no? So 4 unpaired electrons are there. You will fill in like this. 4 unpaired electrons are there. How many exchanges can you do? Either you sit and do like this, 1, 2, 3. 3 exchanges first electron can do. Second one can do 1, 2. And the third one can do 1 exchange. Like this, I think you can do like this rather than remembering another formula and getting confused. Or you can use the formula n minus 1 by 2. Okay, so either way our answer is option D, that is 6 electrons. Did you understand the first question? Exchange energy question is there, part is there in your separate part will be there, no, in your NCERT, like the shaded part, highlighted part. We can't say that it's not in syllabus, so we should consider it. So this question is very much, I'll say, in our NCERT. So let's go next here. Why 4 electrons are present? Look at the configuration. There are 3D4. D subshell meaning 5 divisions we should do. And 4 electrons is given here, 3D4. So how will you fill those electrons? Singly before pairing occurs. So you have 4 electrons then. Next one. E is some minus 78.4 kilocal per mole. And you are asked orbit. What is the relationship between orbit and E? Orbit is represented as N. Orbit, shell, principal quantum number, all mean the same thing. So it's the shell. What is the relation between energy and N? We know that energy can be written as minus 2.18 into 10 raised to minus 18 Z square by N square, right? But then this would be, this formula is in joule. We want the formula in kilocal per mole. That is that 313 number constant. Okay, so let's modify this. Correct. Minus 313 Z square by N square. Now can you calculate, children? Energy is given to you, minus 78.4. This type of problems you should know to do. What is Z here? What is this atom we are taken here? Hydrogen. So Z is 1. So take Z as 1. You need to calculate what is N. So N square will be equal to minus 313 divided by minus 78.4. Approximately you do, children. Normally your all 4 options will be far apart in chemistry. So you should be able to tell the answer. So did we get 4 here? So 7 4s are 28, we can see. So approximately this is 4 here. So n will be equal to 2. Correct? Don't forget it's n square here. So very good, all the children who have answered. So option C, 2 is our answer. Are you all sitting with a book and doing these calculations? Okay. Let's move that. Very great. Okay. Next one. And don't use calculator, you do yourself. If you're taking some time, no problem. You leave the formula, you understand what all to substitute and leave the problem. Later on when you're practicing, you can do that. Let's go next now to the next question number 3. Okay, so an excited hydrogen atom returns to ground state and the wavelength is lambda. The principal quantum number, what is the principal quantum number meaning? N. Okay, some n factor they are asking here. So principal quantum number. Here children, one more thing here. Ground state, when we are saying, basically here we have 2 states, right? One is excited state and one is ground state. Meaning we have 2 levels, we have 2 n's. One is n1 and one is n2. Ground state is a lower level, the normal level. So that's taken as 1. You please remember this. Whenever they are saying ground state, it means n1 is 1. If they are giving you a clue saying first excited state, meaning n2, that is the next level, will be 2. If they are saying second excited state, that means n2 will be 3. After ground state, 2 more. That's what they mean. The reference is with ground state. Here the question is, they have not mentioned which excited state. They're just saying excited hydrogen atom returns. But this we know, ground state they have told. So N1 we know, N2 is what we have to find out. The wavelength we are supposed to assume as lambda only, no values are given. So the principal quantum number of the excited state meaning what is N2 is the question. Why don't you write the formula? Did you get the formula? N1 is there, N2 is there, lambda or wave number is there, meaning it is Rydberg equation. Why don't you write the Rydberg equation? I told you this is important, third most important formula in this chapter. Okay, so we have, don't forget that it's 1 by lambda or 1 by N1 square minus 1 by N2 square. Fill in how much ever you know here. So we know that N1 is 1. Directly I will bring this R here. So I'll make it a little bit 1 by lambda R equal to, so I have here 1 by 1 square, that is 1 minus 1 by N2 square. Just solve this children, find out what is N2. I'll slowly do it here. You also please try it yourself. Did you get the answer? Okay, great. So what we have here is 1 by N2 square. So I'll just make it N2 equal to, invert this. So lambda R divided by lambda R minus 1 and also take the square root of it because it was N2 square. Invert this term and then take the square root of it. A little bit mathematical there. So I got this answer option A. Did you all get option A? That is your N2. So remember all these things. Directly they will not tell you what is N1 and N2 and all. So such type of, clues they will give. You have to find it out. So ground state meaning N1, your first level, is the normal level, which is the normal level 1. Okay, that you remember. Okay, going to the next question here. So 3 is done. Fourth question here. E1, E2, E3 represent the kinetic energy of an electron, an alpha particle, and a proton. Each having same de Broglie wavelength. Lambda is same. So you need to find out what is the relation between their kinetic energy. Lambda is same. So we are talking about subatomic particles. So we are using de Broglie wavelength h by mv, or rather h by square root 2 kinetic energy mass. If you remember that formula, I can use that directly here. So you can see in this formula that kinetic energy and mass of this tiny particle are actually inversely related when lambda is constant. Okay, so what you do, who has here the least mass will be having the highest kinetic energy. Who has the least mass here? Electron. So that is E1. The mass of an electron is very less. Proton is higher. And alpha particle is helium nucleus is what we say, right? So it has 4 as its mass here, AMU. So, and proton has 1, whereas electron mass is considered to be negligible. So therefore, who has the least here? That is option A, E1 for electron will be higher as compared to proton, as compared to alpha particle. Okay, so this is one comparison formula. You can use this to find out that if lambda is constant, then kinetic energy and mass are inversely related for subatomic particles or very tiny particles. Okay, next question here. In a hydrogen atom, an electron jumps from n to n minus 1. The frequency is, okay, so once again, you can see when there are two things given, states given, and electron is jumping from here to there, that means you need to use the Rydberg's equation. So let's write Rydberg's equation. It's 1 by lambda or nu bar equal to R 1 by n1 square minus 1 by n2 square. As it's hydrogen, it's okay not to take here z square. It will be 1. Okay, so this is our formula. Now n to n minus 1. Which do you think is the lower level? N minus 1, right? So you just see and you substitute here. So you can say that 1 by n minus 1 square minus 1 by n square. And you have R here. Now I don't want lambda. I wanted frequency. So what is the relation? C equal to nu lambda. So lambda will be equal to C by nu. So 1 by lambda we have here. So that will be nu by C. So nu by C. Or as I want only frequency, I will send this C here. Okay, so this is what you need to solve. If you solve this, you don't have to exactly find out. Of course, you will not get the answer here because you have some, you don't need the answer. You just have to find out what it is proportional to. Is it proportional to 1 by n4, n raised to minus 4 it is, meaning 1 by n4 is it proportional to, or 1 by n3 it's proportional to, sorry, not 1 by n4. Wait a minute. Yeah, not 1 by n4, sorry. What is it proportional to? Can you solve this and tell me that? So I'll get here, you apply a minus b square, so it will be something like 1 by, or first let's take the common denominator. So n square cancels here. So you get 1 minus 2n upon, I didn't solve this. If you want, you can solve this. You'll get some, basically this also you can solve. You will get some n raised to 4, right, in the denominator. And in the numerator, you're getting some n term. So when you cancel this out, you're getting here 1 by n3. So what's our answer here? Option B. Exact answer you don't have to find out. You'll get a little bit stuck there. So you have to just see what it's proportional to. That's what is the question. Okay, not a very important type of a question, but maybe you have done these in physics as well. So there also it might be helping. Did you understand this? Can we proceed? Two n minus 1 I did get, but then there was a minus sign there. Or did I already consider that? 1 second, I'll check. So I have here, yeah, 2n minus 1, correct. Okay, in either ways, you're getting their n directly proportional to n in the numerator, and in the denominator, getting n to the power 4. Okay, next one. We also have here, we have some 20 minutes remaining, I think. So I also have here, I've collected questions from previous chapters, children. I want you to solve them as a homework. Will you do that homework today, or will you do the questions from homework from educator today? What do you want to do today? We'll proceed with the questions, but previous year questions you should do, right? Okay, then what you can do is you need to take a scan of these sheets. Okay, 15 questions are there. So we will do those. Yeah, is it clear, children? These questions are clear. I've also mentioned the year. It's handwritten, sorry about that, but can you take a screenshot of this or a pic of this? And this is not it. We have 15 questions. So 3 slides are there. Done? You try this. If there is some questions that you can't understand, I will give you the answer tomorrow, and we can also discuss the difficult ones. Done, right, children? Going next. Okay, second sheet. Is it clear? Of course, you can, when you're solving it, you can zoom and see. All these questions are from previous NEET exams from, I think, 2003 to the last year. Okay, they are all in mixed order. These are previous year questions from this chapter. Done? Taken screenshot of this. Next. Yeah, I can also pass this in your group, but then you'll have problems saying this person didn't send me. I've seen lots of that in last time and all. So those people, whoever are there here, please take screenshot. Whoever are there in some group, we'll see that later. Done, children? So total 15 questions. These are your homework questions. If you can get all 15 right, meaning what's there stopping you? You're all ready for this chapter for NEET exam. Okay, let's see how many you get right in tomorrow's class. So I'm not discussing this right now. I want you to first try it. Everyone done? Let's go next now. We'll continue with our problems. It's not like I'm ending the session here. We have a lot of problems to go. Coming to the next question here. Energy of an electron in excited hydrogen atom is given here. It's given in electron volt. And according to Bohr's theory, the angular momentum of this electron is also what you need to find out. So you need to find out the angular momentum, right? And angular momentum is mvr. This is angular momentum. It is equal to nh by 2 pi. Now, h is a constant, you know, pi is a constant 3.14. So n is, if you know n, you can calculate the angular momentum. How to find out n? By comparing energy. You know energy here, can't you find out n? What is the formula? This time you need to use electron volt formula. Try, children, what is that formula there? E equal to minus 13.6, right? This is the electron volt formula. This part remains the same, z square by n square. And z here they're mentioned as hydrogen, so it's 1. So energy is given to you minus 3.4. Can you tell me what is n? So you need to do, yeah, correct. So you all got right, n is 2. Last time also we had got n is 2. Normally n will be 2, 3 or 4 or 1 also it can be. It will not be more than that. So n came to be 2. Now substitute in this formula. So angular momentum mvr equal to 2h. What is h? As they have not mentioned, you take this 6.6 into 10 raised to minus 34. Remember, h is a very small value. Don't make it plus 34. And 2 pi, 2 into 3.14, approximately you calculate. Don't use a calculator and all. 2 of course gone. So 6.6 divided by 3 is approximately 2, right? 6 by 3 is approximately 2. But then we have two options here. Look at this. There is 2.11 into 10 raised to minus 34. And there is 2 into 10 raised to minus 34. Which we should select? Is 6.6 divided by 3.14? Isn't it a little bit more than 2? Little bit more than 2, right? So we can select option A. Just you compare your answers and see how accurate you need to be in your calculation. If you don't need to be very accurate, then you can do. Okay, you didn't understand how we got 2. I'm calculating here. So E you substitute, E is minus 3.4 and minus 13.6, Z is 1 square, and I need to calculate N. So I'm taking N square here. So minus 13.6 divided by minus 3.4. 3 fours are 12, right? Approximately it's coming to be 4. So N will be equal to square root 4, that is 2. Okay. Such type, you're seeing that this relation between energy and orbit, E and N relation is important. So try to memorize kilocal one also, joule one also, and this one also, electron volt one also. You all got the answer? Option A. Next question, question number 7. Energy of 24.6 electron volt is required to remove 1 electron from helium atom. The energy required to remove both electrons from helium atom. So basically you're doing 2 steps. First, you converted helium by removing 1 electron, you got helium plus. Now from helium plus, you're removing 1 electron and you're getting helium 2 plus. This is hydrogen-like. Okay, the second step is hydrogen-like. So you can use that formula there. And here, first step value, they have already given that energy will be 24.6. Energy required to remove electron, that will be positive there. So that's 24.6 electron volt. Now we can use, as it's in electron volt, here we can use this formula, this constant we can use. Energy will be equal to the last one formula, children, minus 13.6 Z square by N square. Now, do we know what is Z? Yes, because it's helium atom. Z is 2. Atomic number is 2. So energy equal to minus 13.6. Z is 2. So 2 2s are 4. And what is N? Which orbit do we know here? we know that may it be hydrogen or helium, it is having only that one orbit, right, from which electron can be lost. Which is that orbit? The first orbit, K shell. So that's why I'm taking here N as 1. Okay, there we have, what's the answer here? 50 something. Okay, something, approximately some 50 something you're getting here, 52 something actually. This is the change in energy, so I'm ignoring this minus sign. And here in the first 54.4, okay, fine, 54.4. Depends how much, look at the answers here. Already I know that it cannot be option A, option B, option C. It has to be option D. Because to this value, I should also add this. They're saying how much energy it requires to remove both electrons. 54.4 is the energy required to remove second electron. 24.6 is to remove the first electron. To remove both, meaning you need to add it. So I know it's going to be more than that 50 value. So I know it's going to be 79. So in such cases, it's okay to not do exact calculation and you can directly do some approximation and tell the answer. So answer here is option D. When you add 54.4 and 24.6, you get 79. Are you all understanding this? 24.6 is given in the question. How much energy is required to remove one electron is given in the question. Question is asked both electrons to remove how much you need. So you calculate for second electron first and then you add both of them. Don't use the word orbital and orbit interchangeably. They are not equal. Okay, maybe for hydrogen they might be equal, but actually they are not equal. So they are the same orbit, correct? Okay, children, so let's proceed next. How did I take N value? I just assumed that this helium or hydrogen will be having, the electrons will be lost from first orbit only, right? Because its electron will be present in first orbit only. So I took N as 1. Okay, next one here. It's slightly confusing, I agree. Very interesting question this is. The radial probability distribution curve, meaning that probability curve which we draw for nodes where we find out the values. It has 3 peaks and 2 radial nodes, meaning it has 3 peaks, something like this, sorry. 1, 2, 3. 3 peaks and 2 radial nodes. These are the nodes. These are the peaks, 1, 2, and 3. Okay. And now you have to tell which valence electron are we talking about? Which orbital are we talking about? So how do we come to know? By knowing the subshell or by knowing the shell. Which is the shell here, children? Can you tell me? Okay, which is the shell? Is it the first shell or the second shell or third shell? How will we come to know? Very good, it's the third shell. How do we know it's a third shell? Because we have 3 peaks here. As soon as they say 3 peaks, it's third shell. That's all. 2 peaks, two peaks meaning second shell and so on. 2 radial nodes are there. Okay, so 2 radial nodes are there, meaning what is the formula for radial nodes? N minus L minus 1. Correct? So radial nodes are 2 and we know N right here. So 3 minus L minus 1. What you get L as? So what do you get L as here? Then you all told some P and all. L is 0 here, correct? So L is 0 meaning, which is the subshell? It is S. Meaning, how do we write this? 3s. So now we know where is our valence electron. Our valence electron is present in 3s. Which of these atoms has valence electron in 3s? So lithium, you know, is like 2s, right? 2s1. So it's our alkali metal which comes below lithium. This is 2s1. So which one we should select? Sodium, right? That is 3s1. And potassium is 4s1. And this is not even an alkali metal. It's going to have 4s2. Okay, that also can be there, but valence electron they're asking about. So anyway, answer here would be sodium. Option D. Did you understand? So with this knowledge, you can find out which is the subshell. After you find out the subshell, you can write down the configuration and see which is matching the last electron. Okay, next one. Explain one more time. Okay. So 3 peaks meaning the shell is 3. 3 shells are there. Meaning the M shell. Okay. 2 radial nodes meaning radial nodes formula is N minus L minus 1. So this is coming to be 2. Now I know N, it's 3 shell. So 3 minus L minus 1 is 2. So L is coming to be 0. If L is 0, meaning it is S subshell. So which is this? N is 3 and it is S, meaning I can write this as 3S. If you wrote as 3s, now you check the configuration of this, and this. Who has the valence electron in 3s? Who has the valence electron in 3s? Sodium. Correct? Because sodium's configuration, its atomic number is 11. If you observe, children, they will not give you atomic number of till like these common ones and all, lithium, sodium and all, they don't give atomic numbers. So you should be knowing, don't think they will give all atomic numbers. D block elements, they may give lanthanoids, actinoids and all, they will surely give. But these and all don't expect. So sodium is 1s2, 2s2, 2p6, 3s1. So valence electron is present in 3s1, the last one. That's how we selected that answer. Very good question. Even I actually got that question when I was telling it to you. If magnesium was also given as an option, what will we do? Then we can't actually say, because exact it would be, right? Magnesium is also 3s2 only. So the valence electron is present in 3s only. Then we can't actually select our answer. Okay, so that's why they have not given here magnesium. Okay, proceeding here. Question 9. We have energy required to break 1 mole of Cl-Cl bond. Some energy we have basically. And that's this much. And wavelength they are saying of breaking this bond. What is the relation between energy and wavelength? What relation is this? Now, energy relation, meaning wave theory we have to go to, that is NH nu. Okay, H nu. Planck's theory. So NHC by lambda. So here I got lambda. Nu I substitute as C by lambda, or you can do it separately. So we have everything that we know, I think. Let's find that out. So energy will be equal to required to break 1 mole of Cl-Cl bond. So energy I know. H I know, Planck's constant. N is okay, I can ignore here. C is speed of light, and lambda here is what we need to find out. Energy we know, lambda we need to find out. So must be simple. Only thing is here, its question is given in kilojoule per mole. Okay, so that you need to be a little careful of. Normally when you say only kilojoule, you mean per atom. This is given in mole. What you have to do, use the Avogadro equation. So 242 kilojoule is for 1 mole. That is, it's for 6 into 10 raised to 23 atoms or molecules or whatever we are considering here. So atoms are right. 1 atom is how many kilojoule, or you calculate joule only. So basically do 10 raised to 3 joule. Yeah, one atom is how many joules? What we'll do, divide, right? So cross multiply here. So you get 242 into 10 raised to 3. Divide by 6 into 10 raised to 23 joule per atom. So this is what we write as only joule. So the answer is here is simple calculation. 4, 1. Yeah, somewhat around this factor. Into 10 raised to 23 came up, became minus. So minus 20. Yeah, you can do exactly, children. I'm just doing here. If you see, I think the answers are far apart, right? I think we can get the answer with approximate calculation. Exact calculation will require time. So substitute this in your energy. So energy is that value. So H is 6.6 into 10 raised to minus 34. C is 3 into 10 power 8. Lambda is what we have to calculate. So what I'll do is I'll take lambda on this side and put energy. What is energy? This factor 41 into 10 raised to minus 20. Children, this is approximately 20. Did you know that? This helps us in calculation. So 19.8 or something like that, which is approximately 20. And this is 40, right? So 20 by 40, I'm just making it half, 1 by 2. That is, I'm taking as 0.5 into 10 raised to, let's check. So plus 20, when minus 20 goes up to plus 20. So minus 30. 6 I got, 10 raised to minus 6. Like this I got. Nanometer you need to calculate it. So 500 nanometer approximately. Because nanometer meaning 10 raised to minus 9. So you need to divide by 3 here and multiply by 10 raised to 3 here. Divide by 10 raised to 3, multiply by, you know how to do that, right? So I'm getting 500 nanometers. So we can select option B here, approximately. Of course, those who are doing exactly will get the answer correctly here.